Good.
Continue. Got it. Oh.
Okay, so we're very pleased to have Wenqing Fan here today to talk with us about new ways to study jet substructure. This is sort of, in my mind, like a two-part talk that started with Ian Molt like 2 months ago, right?
Right, yeah.
So their work is very related, it's super interesting, and Wenqing got her PhD in December 2020 from Stony Brook University, and she's here with us now. So Wenqing, thank you very much for accepting our invitation.
Great, thank you for the invitation, and let me start sharing my slides. And thank you for everyone joining online or in person. Let me go full screen. Okay, can everybody see the slides and hear me fine?
Yep, we see and hear you.
Okay, awesome. So let me just get started. Just as Jennifer mentioned, this is like a two-part talk. Ian gave a very beautiful talk on energy correlators from the theory side, and today I want to offer the experimental view on the energy correlator studies, using it as just substructure observables and then study QCD at colliders. And more specifically, today I want to talk about the results, like two parts of the result. One is the energy correlator results from PP collisions. And the other one is the energy correlator studies in EA collision at the Future Electron Ion Collider. And I will start with the motivation to kind of show why are we interested in it, and try to move to the next slide. Okay, yeah, I think with this audience, I don't have to motivate like too much about like why we're interested in jets. Jets are produced abundantly in the colliders and have been studied a lot, which advance our like understanding on QCD, both in vacuum and also in medium. So we also use this like jet as a probe to study the medium property. And the jets like traditionally like was viewed as a proxy for parton, and you can see that during the jet formation, originally it is produced from some hot process, and then we have a quark gluon going out. But at the end, what we really observe with our detector is a collimated final state of hadrons. And then we have the jet algorithm to recluster these hadrons to kind of give us back this like original parton. But when we look at this jet formation, so like when the quark goes out, it will do parton shower, and then the confinement will take place, and then we have this like final state hadrons. If you look at this process, it actually encodes very rich QCD dynamics, from the perturbative scale to the very non-perturbative scale. And the coupling like runs really from weak to strong. And using the jet as a proxy for parton, kind of we're able to look at the perturbative regime. And recently, like it has become like a popular topic to look at the internal structure of jets. Basically, like the energy deposition pattern, like inside this like collimated final state hadron, to unravel more QCD scales beyond just the perturbative region. And so that's what's so-called like a jet substructure. And here is a cartoon showing that like the different jet substructure observables like can actually access different scales. And today I want to focus on like kind of a new observable, a new jet substructure observable. It's like using the measuring the energy correlator inside jets. So the energy correlator, or say the 2-point energy correlator, it's not a brand new idea. It has been measured in the E plus E minus collider, and it has been used to constrain actually the strong coupling constant. And here, like we kind of use it in a different way, that we're looking at this energy correlator in a collinear limit, like as a jet substructure observable. Here I want to first like introduce you like what is this observable, like from the experimental view, like what we really do to construct this observable is to, we do the jet clustering, we reconstruct jets. And then what we do is we look inside this jet, we look at the constituents inside the jets. and then like make pairs from all those constituents. So it's in some sense like a number of pairs as function of the pair distance, and pair distance is shown as denoted as RL here. But there's like one additional step that makes this observable different just from the pair correlation, which is that we add this energy weight, which is constructed from the energy of the track inside the pair divided by the jet PT squared. And the end, then what we really measure is like kind of number of weighted pairs as function of this angular distance. So it's actually pretty simple if you look at like experimental wise how we construct it. And also like it also has a simple definition in the theory side. So first, this is an infrared collinear safe observable and is well defined in QFT. More specifically, it actually has an operator definition. So really what this energy correlator like measurement correspond to is it corresponds to the correlation functions of the energy flux operator. And so because of this, like, you know, one can actually calculate this observable from first principle. And that's why like during the lab era, people use it to constrain alpha S. And when using this energy correlator as the jet substructure observable, such measurement like the prediction also exists. And later I will show how the prediction look like.
In certain region is calculable.
In certain region, yes. I will come to
Some
that.
region is not calculable.
Right, exactly. I will come to that. That's a good point. All right. So then here's just like a few more words because this is a new observable. So I want to use two other like more traditional jet substructure observable to show like the uniqueness of this observable. So like everybody knows the jet fragmentation function, where like, so this is one type of observable where one measures like what fractional energy is carried by each hadrons inside a jet. And this observable more focus on the longitudinal energy distribution of the constituents inside the jet. And one can go one step beyond, and it has also been this observable has also been used, which adds in the transverse information, so-called jet shape. And what does this observable look at is the energy density at different radial location with respect to the jet axis. So not only you have like the energy, like the longitudinal information, which is the energy, but also you can study the energy as function of R. But in this observable, there is the correlation between the particles or correlation between the energy flux is lost. And that's where like I think the energy correlator like has this unique advantage that we're measuring the kind of the pairs, and we study this cross-section as function of the angular distance of this pair. And the beauty of it is this angular distance RL actually probe a fixed scale when we use a fixed RL. And a kind of intuitive way to view that is to use this like splitting. And so basically the virtuality of this process is predicted to be proportional to the energy scale times the RL. So there is this proportionality between virtuality and RL, and also the splitting time. It's proportional to like 1/ppRL squared. So if we measure this energy correlator cross-section as function of RL, from large angle to small angle, we'll be scanning from the high virtuality, which is a perturbative region, to low virtuality, and also from the early splitting to late splitting.
Then are these two observables complementary, or like do you get everything with the EEC that you had in the jet shape and more?
I think the energy correlator like compared to jet shape has this like preserves this angular correlation. So basically, I don't think one can retrieve this correlation from jet shape. The other way around, if one can actually completely construct this energy shape from energy correlators, that I'm not sure. Yes.
I'm having a bit of trouble with this virtuality estimate. A jet is an algorithm. There's no jet PT operationally. You choose an R and you collect the energy within it. You choose a larger R and collect more energy. Both are legitimate jets.
Right.
But if I just take an event which has some splitting of, let's say, RL of 0.1, and I construct a 0.2 jet and I construct a 0.6 jet. They can have very different PTs, but the same RL. So somehow seems to me intuitively the kind of the QCD hard dynamics is the same, but you're deducing different virtualities. So how does that work?
Yeah, so that's a very good point. So I think here what I want to emphasize is more just this a proportionality relationship between virtuality and RL, meaning high RL is more like high virtuality, low RL is low virtuality. And when one wants the absolute scale from this jet PT, indeed, as you just mentioned, the jet R start to matter. This PT in principle should be the parton energy. And what I get from the jet algorithm, of course, is not really the parton energy. And depending on how big radius I use, by using a small radius, I will lose a good fraction of that energy. But if I stay with, say, a fixed jet radius or say jet definition, I can still compare different RL scale.
So it's kind of the usual QCD business where you want an observable where you can calculate in PQCD and measure an experiment to compare. So this is kind of guidance, but not literal, and it's really the real kind of test comes when you compare to QCD calculations.
Yes, when compared to QCD calculation, we need to make sure that the PT we use is the same. And actually for the calculation that is already available, they can calculate different radius, and that's how I compare. But that's a very good point. And maybe just one more comment, during so this virtuality kind of does not only proportional to some jet PT, but also in the lab error, one can use just a Q square or Q as a kind of reference. So it's not super unique to jet, but it's important to use the same definition between the data and the theory comparison. All right. So indeed, there has already been calculation I mentioned before, and there is also a first look at data using the CMS open data. So this is a caveat of the CMS open data is that it's not really corrected for detector effects, but still we can take a look at this data theory comparison and really see what does this observable bring on table. So this data to theory comparison is shown on the bottom. So the y-axis is this energy correlator cross-section. The x-axis is this angular distance. And so let's first focus on the perturbative scale, perturbative regime, where we can actually make a comparison. So that means we're looking at this large angle region. The CMS open data results is shown by the black points, and then the perturbative calculation or prediction is shown by the blue and orange curve. The orange curve is leading log, and the blue curve is the next to leading log.
Should we be surprised that the NLL and the leading log both seem to have exactly the same average? Was there some normalization there?
Yes, indeed. So the curve is normalized to the height of data, or say the integral under the data in the perturbative regime. So really, we're comparing here is just
So
a scaling.
It's not really a fair comparison.
Well, or in some sense, we're focusing on the scaling behavior or the shape.
But the vertical axis is cross section.
Yeah, the vertical axis is cross section. So the data has the absolute scale, but from the theory, what they do is it normalizes the curve to the data.
Actually, could you go back to your formula, because that's
Sure.
an important point.
Which the definition?
Definition, yeah. So it's really a cross section. So why can't the theory calculate absolute cross sections? You can measure absolute cross section.
Right. I think in principle they can. I'm checking Cal Lee who calculated it is also.
In principle, they can, yes. It's just they're lazy to do it.
I would say maybe it's the next step, but
Not the first time I've heard that.
Yeah.
Okay.
like to begin with, we focus on the shape, but I believe it should be also possible for them to actually calculate this, like the absolute scale.
Yeah, because I mean, if you go back to CMS data, I'm allowed to look at it with my microscope. In fact, the leading log, the orange is a bit below the data, the blue gets better.
Right.
But kind of neither is perfect.
Mhm.
Kind of would like to know what's up,
Absolute scale.
So the absolute scale, yeah, it seems to be important, but okay.
Okay. We can knock them more
Yeah.
to make the absolute.
So the calculation is only about the shape and they ignore the cross section.
Yeah, right now it's more just on the shape and the scaling behavior.
There is a Kyle out there.
Yes, I don't know which Kyle. Yeah, I think
I don't know
this is
either.
Kyle.
Yes.
Right, so Kyle can comment at the end also.
Sorry, I just joined, but I'm on the road. So there's a lot of noise here. Maybe I'll comment later.
Okay. Sounds good. So we'll come back to that.
Well,
later.
sometimes the normalization become important, especially if you want to compare the perturbative region and non-perturbative region.
Mhm.
And sometimes if you are not careful, you are not normalized the same way, you miss some of the shape in this transition region.
Mm-hmm.
And the data are not. The data are absolutely normalized, right?
Yeah. All right. So then for now, we just focus on the shape and the scaling behavior. Like what we notice is that there's like this increasing cross section towards a smaller and smaller angle. And one can intuitively, I think, view that as like, here we're looking at the perturbative regime, basically like, the parton shower, or say the perturbative evolution of like the parton. And then it makes more sense that like we start to see an increasing splitting probability towards smaller angle if you look at this cartoon here. Hence this scaling behavior tells us like we're looking at the partonic degree of freedom here. And now if we look at the other extreme, like the very small angle, the deep non-perturbative region. So the data is compared to this purple curve. And this purple curve is nothing but a linear scaling behavior, which one would expect if you have just like free hadrons populating the whole phase space. And you can see that it's a very like completely different scaling behavior sitting at like a different like RL region. And like this scaling behavior tells us that in the very small angle in the non-perturbative regime, like we're really looking at the hadronic degree of freedom. And the smaller cross section at smaller angle makes sense because like there's a decreasing probability. Yes.
Is that just like phase space then?
Yes, I think so.
It just goes like area, in other words, R squared.
Right.
So it's just a trivial, random,
Right.
uncorrelated distribution. This is what an uncorrelated distribution would look like.
Exactly. Yeah. Of course, we know that like the hadron produced like inside the jet is not really very uncorrelated.
But at some sufficiently
Yeah.
small scale, you should
Yeah.
just see it.
But at very small angle, we see a good agreement, and there start to be deviation. Right. And then now let's look at the middle region. Like now I'm completing this cartoon so that you can see that really this middle region, like what they correspond to, like physics-wise, should be the confinement process. And so basically we see a turnover from the partonic scaling behavior to the hadronic scaling behavior. And it also has been predicted or say expected from the theory that like this transition region should happen when the virtuality approach the order of lambda QCD or say the hadronic or say hadronization or say confinement energy scale. When it approaches this order of lambda QCD, then this energy correlator should like show a transition into the confinement region. So like now we look at this virtuality formula, then that means the position for this transition, which corresponds to the confinement, RL should be proportional to lambda QCD over PT, meaning that we also expect this position, if it really corresponds to confinement, to sit at different location for different jet PT. Yes.
Quick question.
Mhm.
The outside, I'm sorry, I was having trouble getting my mic going. Previous slide, maybe you answered this in this slide 7, but in 6, is there any significance to where the borders of this gray section has been chosen? In other words, has this been calculated from the virtuality or what?
Right, you mean like the width of this transition?
Yeah, each of the ends, each of the limits.
Right. So as for this gray box, it actually like it kind of just placed there like to get the ISO the width like it's kind of random. But from the distribution itself, one can, I think, use certain like using a certain definition, one can actually extract a width. And one way like we're thinking is that like from one can start from like when the perturbative calculation start to deviate from the data, using that as one end, and then like on the other end, like when the linear scaling, or say when the data deviate from the linear scaling, like from the small angle set, use that as the other end, and then like one can actually get the width from it.
And on your 7, I'm sorry, on your slide 7, you kind of head in that direction. But I think you had a formula there too, right? For the virtuality, if you advance.
To the next one?
No. Oh, I thought you had anyway. Right. So here you say virtuality approaches the order of lambda QCD, EUC undergoes transition. So, right, you have RL is proportional to the order of lambda QCD over PT. So I was, again, just wondering whether those borders of your gray section and somehow this formula gave you any sort of information.
Oh, just the formula on this bottom corner, if that one can actually derive the border of like this confinement process.
Right.
That I don't think so.
Okay.
Yeah.
Maybe I have a brain fog here, but I'm not getting that formula. Lambda QCD is maybe a couple of hundred MeV.
I want to emphasize it just
off the left side of the plot. So
that's a good point. So that is just, I also emphasize it's just order of lambda QCD, like kind of.
It's more than an order of magnitude off.
Yeah, that's right. So I can already say that it's actually more like in between 2 to 3 G, not like 300 MeV for sure. So yeah, like maybe order of magnitude larger than lambda QCD. And what we think it really is a confinement scale, confinement energy scale.
But what, I don't understand, sorry, how is it an order of magnitude off? Because you're dividing through by PT jet. Do you have a fixed value of PT jet?
500 GeV.
For the whole plot?
It's right on the bottom right.
Yeah, so this is same as
Okay,
like,
yeah.
So 0.01 is 5 GeV. So it's kind of
200 divided by 500? 0.4?
So 500 times 0.01 is 5.
So, but this is order of lambda QCD over PT. The question is there a precise formula or something closer, something?
right.
If you guys
So
let
maybe
her
I
continue
can-
her talk, she'll give you some data-driven numbers from Alice.
That's a good idea.
Well,
Uh-huh.
can I ask one more question
Please.
about this? I'm sorry, but so that formula you have for RL sort of implies that the transition point depends on the jet energy.
Yes.
So if you have a lower jet energy, it moves.
Yes,
Okay.
that's what I'm gonna show.
Okay.
And
Or if I may comment, like briefly, as Wenqing has on the top of her slides, the real scale that this energy correlator is probing is really the virtuality of the two particles that you're measuring the correlation of. So the scale is really PTRL. And from there, you are able to tune these scales to the scale of your interest. And what you really find is lambda QCD over PT, because the relevant scale that you're really comparing this lambda QCD with is PT times the angle of these correlations.
And I think Raymond also previous on to ask a question.
Yeah, it's very simple. Maybe you can address it when you get to the data. The transition region here is much sharper than I know what our data looks like. Is this just a x-axis fitting difference, or is this really just due to the scale, the difference in jet PT or something?
I think the width is actually similar, so that's probably visual. But we can also put them on top of each other.
Illustration.
Why don't you guys let her show her results and then ask how the show?
Yes.
Somebody else will do that.
All right. So okay. Now if we move on. So what I have shown is just like some analysis like done with the CMS open data with no detector effects correction, and also like one PT range. And now like in the following slides, I want to show you the new PP result from the Alice experiment. And what Alice can bring on the table is that like Alice has very high precision tracking detector, so we can measure like this observable, this angular like distribution with high precision, and also like with the measurement will correct for all detector effects. And also like we made like this measurement in several PT ranges, so one can really see if the transition position actually change as expected with jet PT. And here just like a little more detail of like this experimental result in PP collisions, like it's PP data at 5 TeV, and we use the 0.4 radius jet. And one more thing to emphasize is like we are using the charge jet, and we only look at the charge constituents inside the jet. And when we make the energy correlator pairs, we apply another PT threshold, which is like 1 GeV. And the detector effect is corrected in a beam by beam manner, and overall, the correction factor is actually pretty small, and the uncertainty, the final uncertainty, systematic uncertainty level is around 4% or smaller. And on the right-hand side, I want to show you the result. The y-axis is a normalized energy correlator cross-section, normalized by number of inclusive jets as function of this angular distance RL. And the three curves are shown here, which correspond to three different PT ranges. The blue is 20 to 40, the green is 40, 60, and the red is 60 to 80. And really like no matter which like distribution we choose, we see a clear separation of the perturbative scaling behavior and non-perturbative scaling behavior at large and small angle. And then we see this turnover transition behavior, which corresponds to the confinement. And also what we see is that this transition position actually like shift to smaller angle for higher jet PT. And like we already seen from previous slide that RL should be, this transition position should be proportional to this hadronization energy scale over the jet PT. So for higher jet PT, we have a lower transition position. And the data has also been compared to Monte Carlo models, more specifically Hurwicke and Pythia 8. So here from left to right is the result for like different jet PT ranges from low to high. Data is always shown by black, and the Pythia is shown by red, and the Hurwicke is shown by the blue points. The bottom panel is like model to data ratio, so one can really zoom into the difference between data and model. So actually at first glance, what we notice is that like both of these Monte Carlo models describe data pretty well, both in terms of like the different shapes at perturbative and non-perturbative regime, and also like where the transition takes place. But when we zoom into like really the remaining difference by looking at this bottom panel, like we can see that there actually are difference between model and data, like because these points, these ratio points are not really flat at one. And overall, like from here, we can see that like the Hurwicke describes the data slightly better than Pythia 8. And when we compare data to Hurwicke, like we look at this black points and then these blue points, the data shows a slightly broader width compared to Hurwig.
How are these all normalized?
This here, like the data and Monte Carlo are both normalized by number of jets. So here it's actually the absolute scale there.
Is there some integral or conserved quantity? Trying to derive that from your formula. Couldn't do it in my head. I mean, do these have to add up to the same thing and like integrating over differential cross sections in some sense, or that doesn't apply to these energy weighted?
So you mean
if I take a certain
integral?
So it could go to classic jet shapes. And my objection, you've heard me say this before, is every jet appears somewhere in these sort of classic jet shapes. It's not the case here. And so when you take ratios, you're taking ratios to distributions that all are normalized, to unity. So there's correlations.
Is your point?
Is that applied here, or do you have a freedom?
No, not really, because like so that's also another kind of unique part about this observable. It's not a per jet quantity. So if I normalize by number of jet, it doesn't mean that things has to sum to one. So depending on really what is the kind of total cross section per jet. So there is actually some degree of freedom for that to differ. Right. Okay. Yes.
So both of these models have some deconfinement.
Yes. Yes, and maybe one original motivation for us to compare to this two specific model, not only they're widely used and well tuned, but also that they have different hadronization mechanism in them. So Hurwig used a clustering hadronization model, and PCI used a long string model. So the original idea is to see if the data can differentiate the two. However, from this comparison, I wouldn't conclude that way yet. Yeah. Great. So another thing we can look at is exactly to kind of focus on this transition region. So as I've shown that when we look at just the energy correlator distribution as a function of RL, for different jet PT sample, this transition happens at a different place. And we know that the transition should happen at a fixed virtuality. So we can look at this plot in a different way, that we change the x-axis from RL to jet PT times RL. And also we normalize the y scale so that we're only focusing on the shape of the distribution. So you can see that all the data points, the maximum is normalized to 1. So we're only focusing on the shape here. But when we look at this plot, we can see that actually when looking at the cross-section as a function of quote-unquote virtuality, the shape of a different distribution looks very similar. And this transition really is sitting at a fixed position, and that is about 2.4 GeV. So which indicates really this transition behavior can be really related to the confinement, and there are some universal behavior to it.
Well, this is what I was going to ask when I first discussed. First of all, in principle, such energy correlation should have some kind of scaling behavior at larger angle, not at a small angle. And is that the scaling behavior in terms of angle or in terms of virtuality? Now it looks like it's scaling like virtuality, like PT times the angle, right?
Right. Yeah, I think if we just
this Kyle might be able to answer. In their calculation, I would imagine it would be scaling like angle instead of the virtuality here, because here you are do arbitrary factor normalize everything. But in the actual calculation, in theory, what the scaling variable should be.
So the actual scale that comes out is the virtuality. Virtuality is always the fundamental quantity that comes out in the calculation as a combination. But we just chose to plot it in angle, and then as you can see in the right plot that Wenqing made beautifully, it shows that really the fundamental quantity is the virtuality that you're probing.
Why should the large angles also be correlated? Are you talking about back-to-back, not be correlated, have scaling behavior? You're talking about back-to-back partons?
Yeah, well, here, it's just like, there's, I'm just wondering whether there's any scaling behavior. And Carl said there should be should have scaling factor as proportional to the virtuality instead of the angle. I understand that it's especially at very small angle, right?
By small angle, you mean like here,
Yeah,
like 10 to the
large
negative.
angle, sorry.
So here, I would also still say that even the large angle region here is a pretty small angle, right? This is actually really inside all jets.
Yeah,
So
yes,
it's still described by the collinear limit or collinear splittings. And what you can actually show is that the scaling region or the partonic splittings are determined by really DGLAB-like splittings. So here, the anomalous scaling of this partonic region is governed by really just the moments of the DGLAB or arbitrarily Parisi splitting functions.
Yeah. Okay, I'm shut up because otherwise when they're finished.
Yeah, we can have more discussions later for sure. Okay, so then like this is now like comparing like different scaling in different region now with this like fully corrected data from Alice. And to start, I just like choose one jet PT being 20 to 40 GeV and cross section function of RL on the right hand side. So the large angle within jet radius, we have the perturbative region, and it's compared to the NL calculation from Carl. And we see a good agreement. And on the left-hand side, like we see that this linear scaling from free hadron model, like agree well with the data. It's a very small angle.
I'm sorry, I want to come back to the previous one. It's related to
this one.
Related to the question I asked at the outset. So there are measurements from Alice primarily, which show very beautifully that the production cross section for small versus large, and James did this for his PhD, for instance. If you just take the inclusive cross section of proton collisions as a function of PT, you take the ratio of cross section for smaller over large R, it actually grows with PT non-trivially up to 50 GeV. I know this is charged, not full, but it's still there's a growth. So that tells us things that we kind of knew from LEP, is that actually the whole kind of structure of jets is changing non-trivially over the region, say 20 to 50 or 60, which is the reason you're measuring there. So I kind of want to come back to my initial question about PT. So you're choosing, R.4.
Yes.
That's a choice, and you see this beautiful scaling. But if you would choose R.2, and as Kyle remarked, and we see, I mean, this is 0.1 radian, so it's a tiny, it's a small angle. If you choose R.2, you would get a different jet population. I wonder, have you tried this scaling with different R's and see whether it really holds? Because it's somehow the R of the reconstruction and the kind of the small angle virtuality is kind of getting mixed up here in a way I'm having a hard time sorting out.
So we haven't tried different jet radius yet, especially for a very small radius, if that's what you're asking. And I think like we can certainly try, but what I would expect is like, I think the scaling behavior, like, this falling shape should stay the same, while like there may not be as good of the overlap when I change the x-axis from RL to PT, because as you mentioned, if there is like a PT dependent jet energy ratio from large to small radius, that then can come in to this point. Right?
It'll also shift the peak if it's 2.4.
Yeah, the peak can I think differ.
So the scaling is good, but the absolute seems to be kind of a choice, not a. So where the peak is kind of a choice of your analysis. You could shift that, but
so I would say.
Right.
Sorry if I may interject. I would say if you actually plot it as a virtuality, you'll still see the peak at this exact same position. The only thing that would change is, normalization and also where you cut off on the right. So you'll see the exact same scaling region within the the overlap region where you see, for instance, if you compare 0.2 and 0.4, the correlation at 0.1 around that region would be exactly the same for two different jets of different radius. It's just as you get to the edge, you start seeing the edge effects where you now have a correlation that are of the size of the actual jet radius. But away from that region, if you're sufficiently looking at probing the small correlations, those would be pretty robust. Because a very small correlation really doesn't see the jet boundary.
But say like I use a 0.1 radius and I only capture say 60% of the energy of the radius with 0.4, wouldn't that then shift the whole peak to a lower energy?
I don't think it will shift the peak.
Oh, it won't
really
shift the RL, but I think it can shift this PT times RL plot, right? Because this PT it's something constructed with a fixed radius.
Oh, you mean if you
Yeah,
check?
that's kind of my point, yeah. I'm sorry, I didn't mean to do it. It's super interesting. I just kind of got stuck on this point, so let's go on. I'll wait till the end to ask more questions.
Okay. All right, so then like this one I have shown, so I won't go through it in too much detail. And here is just like a more complete set of the comparison with theory in all different PT ranges, from low to high PT range. And we can see that like in each PT range, we have a good agreement with PQCD at a large angle and a good agreement with a free hadron scaling at a small angle. And then like in the middle, this like transition or say confinement region, like there is deviation. And so now I want to switch gear a little bit. So I've shown you the PP result, which kind of tells us like the really we see this energy correlator allow us to image this jet dynamics from high to low virtuality in vacuum. What about in medium? Especially like how will medium modify this jet dynamics? And one can actually, and there are two types of medium, of course. Like I'm gonna today focus on the cold nuclear medium and with an outlook to the hot nuclear medium. And for the cold nuclear medium, like very good system, like ideal system one can study is actually the EP and EA collisions. And then like the questions I want to pose before showing any result is that will we also see the scale of hadronization in EP similar to PP? Will we see the interactions like between the jet and the nuclear medium like imprinted in this energy correlator? And also like there, because like we're introducing this like cold nuclear medium with a fixed size, can we also see the scale of this nuclear medium in the energy correlator? So that's a question I want to pose, and I hope like later with the results, like I can show that this question will be answered. And to study this electron ion collider, it's an ideal facility. And here I pull a quote from the EIC white paper. This is also like an important part of the EIC's science program to study how the color charge interact with the cold nuclear matter. And one brief slide on the EIC and the detector that will be used for the study. So EIC is like very versatile and high luminosity machine, and different beam energy can be run. And also very important to us is like EIC can provide a variety of ion beam. So really for the EA collision, like we have EP collision, and then like can also have E deuterium, E helium, all the way up to potentially E uranium collision. So actually with this system, you can control the medium size. And with a high luminosity, you accumulate a lot of statistics, and then like to do the final measurement, we use this EPIC project detector. And this detector features a very precise tracking and vertexing system, so like very good for this measurement, and also it will have a very wide coverage. Okay, and EIC is not built yet, So like right now, we don't have data to analyze from EIC. So what we really like look into in this case is the simulated events using the e-hygiene event generator, and she knows more than me. So this e-hygiene event generator is developed to study like nuclear modified jet evolution in DIS events. And with these two cartoons, I want to kind of like illustrate like really what's the difference, like what e-hygiene brings us. So for the EP collisions, we just use we usually just use PCR8, and e-hygiene will default to will actually come back to PCR8 if one runs the EP collisions. And what process is simulated here, or say generated here, is just the hot DIS process, and then like proton going out and hadronized using the PCR string hadronization model. And then e-hygiene, like for the EA collisions, like what's added in addition is for the initial DIS process, like when we'll have like the nuclear PDF effect, isospin effect, and such. And most importantly to our study, there is also effect of like the medium modified proton shower, including the PT broadening and also medium induced proton splitting, shown by this bottom right cartoon. And before showing any result from the maybe one other thing I forgot to mention is that like this is not just a random event generator. It's actually benchmarked to the Hermes results. So it's actually a reliable event generator that reflects reality. Before I show any results, I want to then like come back to the observable and introduce a new knob that we can use with this energy correlator. So if we look at this like formula of the energy correlator definition for the PP studies, for the energy weight, what we use is just like the PT product of the two track over the PT square of the jet. And that basically means like if we add a power here, like the power used for PP collisions n equal to 1. And with this n equal to 1 energy power, it suppresses the soft contribution from the background by this energy weight, and one does not need to do any grooming when compared to the PQCD calculation. But one can actually change this like power of energy weight. And one way is to increase it. What that will do, it will further suppress the soft contribution, and it can be very useful when one look at the large background environment like AA collision, the heavy ion collisions. And one can also decrease it, and that can enhance the sensitivity to the soft contribution, and that can be important when the signals is in the soft sectors and the background is very small, meaning that we have a clean environment. And that's exactly the case we have for EP and EA collisions.
By the way, I just realized that in the formula, that energy correlate because you divided by the energy of the jet.
Yes.
So that's essentially just momentum fraction of Zi jet.
Right.
Right.
Yes.
Is that true in your analysis? That's momentum fraction. You know, if you momentum of the energy of the particle divided by the energy of the jet, right?
Mm-hmm. Yeah, it's basically Zi times that, right? Mm-hmm.
But there's an IJ in there.
IJ is different two different particles.
Yeah, two different particles. So yeah, basically like PTI times PT jet is the Zi and then the other one. Yeah. Right. Okay. And now like so with a clean environment in EPA collisions, and by clean I mean like we have less background compared to PP collisions like pile up, multi-proton interaction is just not here. And so we can actually tune this energy weight power to smaller number, and here the result I'm going to show you is with n equal to 0.5. And for the EP and EA collision studies, because we have this like wide coverage detector from EPIC, we go for very large radius. So here the jet radius is chosen to be 1 here. Okay. And then like here, like on the bottom right, basically I show you the e-hygiene EP results, or in some sense like PTI EP results. The y-axis is the cross-section, correlator cross-section, x-axis is the angle between the pair. So So I used to use RL and now it's changed to theta, but they mean the same thing.
So this is deep inelastic scattering, so why do you need jets at all? Why don't you just use Q?
That's I think we can also use Q, right? Yeah, meaning like change
It would
this
then be
definition.
kind of a global observable of the entire event.
Right, yeah, that's true. Yeah, here we kind of more focus on the collinear limit of the line with the outgoing parton, but one can also get the direction of that from just the DIS kinematics and using the Q sphere.
You can
That's
boost
a
to
way.
the bright frame and just measure the current hemisphere, and that then is equivalent to a jet finder.
Mm-hmm. Yeah. I think that indeed we can also do it that way. Here we choose to use a similar definition as the PP case. Right. Okay. So then like here, we also see in the EP case that there is a different scaling behavior at large angle and small angle. And that's indeed like what we have seen in the PP collisions. Now I want to show you what does the medium do to this energy correlator distribution. So basically the EA results or say ego results is shown by this more colorful curves, and the baseline EP is shown by blue. And what we can see that because of this induced parton splitting caused by the presence of the medium, we see some difference between the EP and EA distribution, and more specifically, we see an enhancement of the distribution, or say the cross section at large angle. And that makes sense because we know that for the large angle, it corresponds to the earlier splitting. And with the nuclear medium here, one would expect that only when the splitting for the splitting that happens inside this nuclear medium, it will be modified. So for a very small angle, everything happens outside the medium, so nothing happens. But for the large angle, for the early splitting, when it happens inside the nuclear medium, we see a modification, or in some sense, it's actually enhanced.
How did you normalize this for different direction?
Right, so the normalization is done the way that all the EA result is normalized to EP in the very small
Okay, so
angle.
this is sort of arbitrary normalization.
Right. Yeah,
That's right.
kind of based on the assumption that the shape and the small angle is not modified. Yeah, and here the different EA results has different transport coefficient that is controlled by this K factor. The K factor equal to 4 is the default setup, which is benchmarked to Hermes data, and then one can change it to slightly smaller number and larger number to control the Q hat. And we can see with larger Q hat or transport coefficient, there is a slightly larger amount of enhancement. All right. And as mentioned that we have this additional knob to control the energy weight, this n factor. So we also look at how the modification will change when we use different n. And here the y-axis now is just the modification, the relative size of the modification defined as the difference of the distribution EA minus EP divided by EP. So the unit will be percent. And the x-axis do the angle, and we can see basically the ratio being larger than 1 means that we see the enhancement. And what I showed in the previous plot would correspond to this red curve. And the other curves correspond to when we tune this energy power to higher and larger number, and we can see with a larger n, we see a smaller size of the modification, which makes sense because the effect of the medium is that it induces more soft radiation. Hence, if we tune the n to smaller power, it will give us more sensitivity to such modification. Another thing I want to emphasize is that you can also see the modification actually is most visible at very large angle. So we're looking at the jet radius equal to 1, we can see the multiplication is most visible between 0.5 and 1. And we're actually also looking at a 6% multiplication, so it's not a huge effect. But with the statistical precision, they should be measurable with EIC. All right, And then like one other thing we have checked is how does it scale with different jet PT? And so basically, as I have mentioned before, like the reason for this enhancement showing up as a large angle is because like this large angle splitting corresponds to very early splitting that takes place inside the cold nuclear medium. Hence, like really the onset of this modification should correspond to when the splitting just happens around the edge of the cold nuclear system. And if like we recall that like the splitting time, it's proportional to like 1 over PT like theta square, the onset angle should scale as like 1 over square root PT times RL. So basically this onset angle should actually change for different jet PT. And to really like view this scaling behavior like more clearly, we just change the x-axis from theta to theta times PT. And in this times square root PT, and in this case, if it indeed scale this way, all the curves should, all the modifications should show up at the same onset position. And that's indeed what we see. So here is still only the relative modification as function of theta times like jet PT, square root of jet PT, and we're looking at different jet PT from 5 to 10 GeV all the way up to like 20 to 30 GeV. And we can see that with this new x-axis onset angle is like seem to show at the same position for different jet PT.
Did you also change the Q squared range? Because the Q squared range that will produce a 5 to 10 GeV jet is somewhat different from that will produce a 20 to 30 GeV jet.
The Q square range we used, or say like when we generate these events, we have a Q square larger than 10 GeV cutoff to just more efficiently generate the events with energetic jets. But like if you are talking about if I select events with this different jet PT, their Q square profile will be different. That's right. Yeah. Okay. So we see this. Yes. So we see this scaling behavior like with different jet PT. Another thing, like I mentioned before, like with EIC, one can do a lot of like type of EA collisions from E helium to E uranium. So one actually have a good control of the system size. And this onset angle should scale actually as 1 over square root PT times the nuclear medium size. And the nuclear medium size should be like more or less proportional to the atomic number over like to the power third. So there's also a relationship between this onset angle and the medium size. So we can use our old trick one more time and to check if this scaling behavior indeed is there when we look at this like modification as function of different system size. And that is like kind of what this bottom right plot is showing. So on the x-axis, it is a to the 1/3 times theta times square root PT. And if the onset angle scale as what we expect, then different like EA systems should give a similar onset angle. And we can see, although not exactly the same, but they look actually pretty similar when we scale it this way, meaning that we do observe such scaling behavior as function of the system size. And now I come to my summary. I have, I think, run significant overtime. So I will maybe just like highlight one thing that like for the cold nuclear, to study the interplay between jet and the cold nuclear medium using this energy correlator, not only one can do it in the future EIC, but one can also use existing PA collision data. And there's ongoing analysis with PLAD data from others, so stay tuned for that. And also, of course, it'll be very interesting to look at if the scaling behavior also shows up in the hot nuclear medium, the QGP. One can study that with the AA collisions. That's all I have. Thank you.
Thanks, Paradox. That was an excellent seminar, Wenqing. So we have questions. I'm gonna grab, so it looks like Feng was first.
Hi, Wenqing, very nice talk. So can you go back to slide 19? I have a very stupid question.
This one?
Maybe one more back. I don't remember. You have different PT bins.
Different this one?
Yeah. So for example, if a PT bin is 5 to 10, R is equal to 1. So how you get a theta square root PT up to 5?
So you mean for this blue curve, how can they get it up to 5?
Yep.
So basically, like I think the hard cutoff should come at like 2 times jet R, right? Like the diameter. I can have a pair with distance as big as 2 times.
Okay.
That's why it comes in. But you can see it already fall off before that, and that's where the jet radius sets in.
Thank you. Another question, maybe this to you and both you and Kyle. So you tune the N, right? So that's basically the power. So N equal to 1 is normal energy correlator. N equal to 0 is like you previously introduced the
just a pair distribution.
Yeah, just like normal whatever previous event shape observable. So if N equals 0, I believe there will be soft ground radiation contribution that will cause some inverse safe problem, right?
Right.
So here's the question. So to what value of N you can still have inverse safe? I mean, N equal to 0.5 looks okay. I mean, the question that is if there is a critical number of N that you cannot really predict it from the continuous splitting anymore.
That's a very good question. My answer is like, my impression is only N equal to 1, it's IRC safe. And for N equal to 0.5, it's already not IRC safe, but maybe Kyle can add if that's really correct, and if there is a critical value for N.
Yeah, I think what Wenqing said is exactly correct, that actually only N equals 1 is IRC safe. But if you choose different N values, the question is whether it's a IRC breaking in a controlled way. And that is, you can actually capture these non-perturbative effects with moments of fragmentation functions. So for instance, N equals 2 is just going to be higher moments coming in fragmentation functions. And N equals 1, even the way you actually show that it's IRC safe for N equals 1, if you incorporate hadron or fragmentation, is that it's just by some rule, the fragmentation just becomes 1. So N equals 1 in that sense becomes IRC safe, but other moments do not, because Z is it's by energy conservation 1, but Z square or Z to the half power is not.
So let me follow up, Kyle. So in the sense that for N equal to 0.5, you actually don't have a reliable prediction? Or you do,
I think
but you have to take into account additional resummation effects?
After you take into account the moment, if you input the moments of the fragmentation functions, then you can calculate this. But yeah, so the perturbative splitting would all be there. The resummation will be all perturbative, but there will be a non-perturbative input.
The fragmentation function one comes in.
Exactly.
Oh, okay, good. Thank you. No more question?
Okay, Peter, Spencer?
Yeah, I've asked lots, so Spencer, go ahead.
I had a question, I just probably best applies to a lot of things, but maybe one of your Alice slides. So you talked about, the distribution on the left being, the free hadron scaling. So does that, at what level would things look, any of these math are fine, would things look different if you looked at, same charge versus opposite charge, where you start to see things like resonances, etc.?
Yes. So indeed, right now what we have is just all charge combinations, but there's actually ongoing calculation, and also with the data, we can actually separate like sign and I like sign. And it will be interesting, I think, like how the distribution look like for both like the transition region and also like the hadron region, if we see like the HBT effect or like resonances.
I mean, is there any, anybody have any back of the envelope thoughts as to how big an effect it is?
Kyle actually already have some calculation on the perturbative regime, and one can also do such like analysis with just Pythia. And maybe Kyle can comment more, but like basically like for the transition region, there is a visible difference for the like sign and unlike sign. For the hadron region, like we don't see a drastic difference between the like sign and unlike sign. Yeah.
Surprising, okay.
But also like what PPI gave us, so it'd be interesting to see the data.
Actually, can you go to your last Alice slide before you went to the E's? Yeah, there we go. So yeah, so you had to go a little quick because I was asking way too many questions, but now the talk's already asked my question here. So you were very clear and that the theory and the experiment, there's non-perturbative scaling between them.
Right.
So and what one wants to do is compare the shapes.
Right.
So let's set aside the pink. And well, actually, I mean the pink is just geometry.
Right.
And if I look at the middle and the right, the pink doesn't do great, but the perturbative also not so much. The shape seems off to me. Am I being too pessimistic, as is my nature? But the normalization is the one is arbitrary.
Right.
It's clear. So all we know is all we can compare is the shape, and the RL dependence seems substantially different.
Right. So basically, like Peter, you're asking like if I really look at the ratio of the PQCD and data, like it's close to 1, but it's not really flat at 1.
Well,
There
it's
is
not
a
even the one.
difference.
As I said, the one is arbitrary, so it's really only the shape we can talk about sensibly, and that seems off to me.
So I think like right now the calculation indeed is just like anchored to the data. So it's like kind of random normalized. But it should be possible, I think, for us to have just absolute like comparison between the calculation and data, if that's what you're asking.
No, I'm asking the opposite. I'm saying to take the middle one where the precision is best.
Right.
The orange, it's a U shape.
Yes. So okay. So that I think, so on the
Yeah,
large
maybe.
angles, yes, please.
Sorry. Well, first, I would argue that it's still within the theoretical uncertainty, but of course, we are trying to calculate to higher precision. And the other thing is, and I think many people noted this already, that non-perturbative effects will be still present in this perturbative region indeed. And they actually fall off much faster than the perturbative effects. So as you go to higher angle, you'll see less and less non-perturbative effects, but these are also going to change the shape slightly. And I can't say whether that is really what you're seeing, but that might be one source of the reason why there's that like non-trivial shape dependence. And then on the far right, that's also expected in the sense that this is really getting close to the jet boundary. So if I have a really large jet, then maybe you'll be able to control the right side better. But on the left, I think that's sort of expected from the power corrections coming from non-perturbative effects, which is also something we're thinking about.
So Kyle, is your theory band, should I understand that as being correlated? In other words, that's an uncertainty of the normalization, but not the shape, or is there some RL dependence in the theory band?
Apparently not.
Let me get the answer from Kyle. It's important.
It's just a scale variation.
That's right.
Just
So I can move it up and down, but that's kind of an arbitrary thing.
But the non-perturbative effect, which is not accounted here in this calculation, can actually introduce some like RL dependence.
Okay, good. So you're saying if there's a non-perturbative factor, which will,
Right.
when accounted for, will change the shape of the theory distribution.
Right, and this non-perturbative effect is something that people understand very well. It's corresponding to the usual like jet thrust, jet mass, ungroomed jet mass type non-perturbative corrections, which is easily accountable, but it's just not out yet. But we're thinking about doing that too. Yes.
Yeah, let me ask this. I'm also worried about this normalization. The fact that you said that there could be non-perturbative, but that's not the reason you cannot really have an absolute normalization, because the non-perturbative region only comes in the close to the peak. But as you said, at large angle, the non-perturbative effect should not be very important. So what?
Yeah, it's a power correction.
Yeah, what prevents you to have the absolute normalization of this calculation?
I mean, I would say it was the easiest thing to do, but it's definitely easy to do.
Number of pairs. It's just number of pairs weighted by the energy, right? There is no reason you cannot have a complete.
Absolutely. Absolutely, you can fully do the full perturbative cross-section calculations and normalize it by that. And that's one of the beauty of energy correlators. Actually, if you normalize by the jet cross-section, it will be always integrated to 1 if you actually integrate over the angle. And that's because if the sum of these energy that you're weighting by is just total energy of the jets, so it just cancels in the fraction. So there's no reason why we didn't do it. You could definitely do that. But when we first wrote this paper, it was at 500 GeV, which you will just not see anything by.
The reason why I'm insisting on this, because you know that once you introduce another scale, for example, heavy quark mass, you know that this will be different depending on the mass, and then the only region that this converges, this different mass will essentially scale is at a very large angle where the mass is no longer a very large scale, no longer important. So that's why it is important to actually have this normalization.
Absolutely, and we have actually wrote a paper on massive energy correlators as well. So.
We're going to Barbara. I think Barbara had a question earlier. Do you still have a question, Barbara, or no?
No, I was going to make a comment, but Kyle already made it.
Okay, awesome. Peter.
Speculate, does it make sense to just think about energy correlators for room jets to cut away some of the non-perturbative physics?
I think one can do that. My naive expectation is that it won't make difference because the soft contribution, the things that will be groomed away is already energy suppressed in this observable.
I guess that'd be maybe a question of Kyle. Is that a theoretical interest, or is that just random physics?
I second Wenqing's statement. In some sense, these perturbative calculations, these non-perturbative effects that we just talked about, and also Xinyan commented on, is completely power corrections. So there's no reason to groom it in that sense.
Well, would that be a useful test?
Yeah, I mean, yeah. If you groom it, you'll still get the same thing, I would imagine.
I didn't hear a reason not to do that.
Okay. Yeah.
I'll give you a reason not to do it. If you if there's a bunch of work and you get the same answer, why do the work?
Because if it gives you a meaningful check on your formalism, that's a reason to do the work.
Well, I think when she said right, you groom away only the soft stuff. The soft stuff does not have much contribution to this anyway.
I mean, yeah, if you want to, I think you can test on Pythia. But yeah, I mean, if you go to very small PT jets, then you'll see some effects possibly. But in principle, these energy weightings will take care of these non-perturbative effects already.
Well, guys, so anyone who wants to stay, please stay. But let's thank Wenqing for our
think I see your hands up.
Yeah, so
I
also
would
had a stupid question.
I would actually expect, I would expect affect resonance instead of I don't think thrust.
What do you mean? You say expect resonances to have-
So you have a jet, you have a bunch of particles. Many of those particles are low flying